All right, here's a couple of gas law questions. First one was the ideal gas law, and then I forget what the second one was about. Anyway, first one, a vessel contains, let me just write this down. Vessel contains, I have a volume of 11.6 liters, and it contains 2.8 grams of nitrogen, so many grams of hydrogen, 79 of argon, and the temperature is 25 degrees Celsius. So 25 plus 273.15, that'll give me 298.15. Is that right? Yeah, I think that's right. Kelvin. And they say, what's the pressure inside the vehicle? So it's sort of a three-parter kind of question. And what you could do is just figure out what the pressure is due to nitrogen, and then the pressure due to hydrogen, and then the pressure due to argon. But it's a little bit easier if they don't need to know what each partial pressure is. It's easier just to find the moles of each of those. So find the moles due to nitrogen and to hydrogen and the moles due to argon, add them together, and then use that total number of moles to determine the pressure inside the tank. And I think that's the way I'll do it. First off, though, I have to figure out moles. So let's figure out moles of nitrogen. So it's going to be mass over molar mass. The mass, they say, is 2.80 grams. And nitrogen is 14.01. But since it's N2, I need two of those. So that'll be 28.02. Let's do that on the calculator. 2.8 divide 28.02. So I get 0.099928, etc. 286, we'll say. Okay, and that is moles of nitrogen. Let's do now moles of hydrogen. So moles of hydrogen, mass over molar mass. The mass, they say, is 0.403 grams. And the molar mass of hydrogen is 1.01. And since it's diatomic, this will be 2.02. Okay, calculator. 0.403 divide 2.02. Whoops. Okay. So from that, I'm getting 0.1995045, etc. moles. That's hydrogen. Now let's do moles of argon. Oh, I got to figure out the molar mass of argon. Just a second. Got it, 39.95. 39.95. And I have 79.9 grams of that. Okay, divide. Okay, 79.9 divide 39.95. Oh, it's exactly 2. Interesting. Moles. Okay, so that's the total number of moles of gas. And we know that when gases are in a tank, that they all act the same. So what I can do is I can just add up that total number of moles. So, so I'm going to add all that up. I think it's going to be 2.2, 2.3 something. But let's add it. Okay, 0.0999286. Plus 0.1950495 plus 2. Okay, so the total number of moles then is 2.2943355. That's total moles. So now that I have all the moles, I can do my PV equals nRT thing. So PV equals nRT, and they're wanting to know what pressure, so this is what they're looking for. I'll divide both sides by volume. So pressure is equal to nRT over V, moles, 2.299433355, etc. Moles times 8.314 kilopascal moles per Kelvin, kilopascal liters. That unit wrong. Kilopascal liters per Kelvin mole times the temperature was 298.15 Kelvin and volume 11.6 liters. Okay, so liters cancel, Kelvins cancel, moles cancel, left with kilopascals. Perfect. Okay, so now I have to multiply all that stuff. Okay, I'll maybe take that number that I had up there. I'm just going to put that in brackets. Maybe I can't. Let me scroll down a bit. Here we go. So, 2.29943355 times 8.314 times 298.15. 8. Good. Divided by 11.6. 491. So the pressure, I'm saying, is 491.37-ish kilopascals. In terms of sig figs, let's check that out. 3. The temperature's only 2. So I could go 490 on that. Oh, but I have kilopascals. They want the answer in atmospheres. Oh. Okay. So I have 491.37 kilopascals. To convert that to atmospheres, it's 101.325 kilopascals for 1 atmosphere. So I just have to take that answer that I got and divide it by, let me put a bracket there. Bracket at the front. So I'm gonna, oh, it all went away. All right, so I'll just type this in. 491.37 divide 101.325. 4.85, something like that. Right there. That's the one I'd pick. Okay, that's the first question. Let's see the next one. Consider a sample gas in a container comfortably Chicago. Celsius temperature suddenly doubles, and you transfer the gas to a container with twice the volume of the first container. If the original pressure was 13, what is a good estimate for the new pressure? Oh, well, let's see here. Whoops. V1, P1, T1, N1. Oh, we don't lose any gas, so I don't need to have that one. But I need a V2, P2, and T2. So they say the original pressure was 13 atmospheres, and the Celsius temperature doubles. So I'm not sure how I would write that. Let's write it like this. So the Celsius temperature, let's call it X. So, but that's in Celsius, right? So I'd have to go X plus 273.15. And so the second temperature will be 2X plus 273.15. Okay? And they want to know estimate for the new pressure. And the volume, what happens to the volume? Transfer the gas to a container with twice the volume of the first one. So say the volume is Y, then this one is going to be 2Y. Okay. So if I did my V1P1 over T1 equals V2P2 over T2, I'm looking for P2. So P2 is V1P1 T2 divided by T1 V2. Okay, so V1 is Y, P1, 13 atmospheres, T2, 2X plus 273.15 over T1, X plus 273.15 times V2 is 2Y. Okay, so the Y's will cancel out. I'm just trying to see. These things here are going to be fairly similar. But this doubling the temperature might increase it a little bit. I'm not sure how much it would increase it by. But then you divide that by 2. So they're saying a good guesstimate. Well, I'm adding a little bit more here. So it should go up a little bit from 13. I don't know how much more. It should go up a little bit, but then I have to cut it in half. So like half of 13 is 6.5. Gee, I might go right there. And they just say find a good estimate. That's probably what I would estimate. Like it's not going to double. It won't stay the same. And I don't think it'll go so small like that. And it won't get any bigger. I think 7 is probably a good estimate. All right, hopefully that helps with those 2 questions.